Your book, your homework was from a section. The homework from last time was from a section called Second Degree Equations and Systems, and I didn't assign any of those as homework because your book has split this stuff up into basically two different things. I want to present them as one thing and one method of dealing with systems of equations. So that's kind of what we're going to talk about today. You're not going to have any stuff from 10.6 because 10.7, which is what we're going to be talking about today, is pretty much the same thing, but it says to solve using a different method. And what I'm going to do, I like the way that I've been doing these forever is a kind of a combination of those two methods. And so that's how I want to present this. That's how I'm going to recommend that you solve these types of things. So first question, what's a system, right? Well, so this is the goal for today. We want to find the intersection of this object and this object right here. In other words, now that's how I put it right here, the intersection of this. Your book, and I'll also say it this way, to solve the system. You're given two equations. That's a system of equations. And we want to solve the system. That means the same thing as find the intersection of them. Now, we've seen this before, right? To solve this system, given two equations like this, means the same thing as find the intersection of them. And the way that we've done these, when these are linear systems, when the things that we're working with is lines, we said, well, we could think about this like this: x plus y equals 1, x minus y equals 1. We could take this information and represent it in a matrix. We say, all right, that means 1, 1, 1 on the top, 1, minus 1, 1 on the bottom. And we could go through and solve this. I'm not gonna talk this through. I'm just gonna go do this. Hopefully I don't mess it up like I did the last time I went and solved one of these on the fly. But this should work out to a 0, and you bring that down for a -2, and you bring that down for a 0. And then let's see, this thing right here is the same as 0, 1, 0. I'll just divide everybody through by -2. Okay. And then I could take that and subtract him off. And so I end up with 1, 0, 1, 0, 1, 0, which means that these two things intersect where, let's think, this top means x equals 1, and this bottom means y equals 0. So it should intersect at x equals 1, y equals 0. It's one way. That's the general way that we've done when we're given a system of lines or a system of linear equations. And it is, I think, the most straightforward way of dealing with this. So, however, there's two other ways that we could have dealt with this linear system right here. We could have said, well, wait a second. Let's look at this guy, x plus y equals 1. I could solve that for y and get y equals minus x plus 1. I could take this guy right here, x minus y equals 1, and I could solve for y. I'll bring the y over to this side this time, and that gives me x minus 1 over here. And so I have two lines. And what I could do, if I'm adept at graphing, which I'm not, but if I could graph really, really well, I could say, okay, this one right here goes through the x-axis the y-axis up here at +1, and it has a slope of -1. And so it comes down, and now I don't have to use my brain because I'm thinking, well, if you go over 1 and down 1, because the slope is -1, then you must go through here at 0. I'll label him, I guess, right here with a Z. Oops, that's not a 0, that's a 1. Oh boy, I need to have more coffee before I try to attempt that. That is when x equals 1 right there. And that is also where y equals 1 up there. This guy right here is the equation y equals mx plus b. So -1 is where it goes through the y-axis. It has a slope of +1. And in this case, I don't need to use my brain. It just so happened to work that I really don't, I could just do this by seeing it. Like, yeah, that has a slope of +1. It goes up. For every one I go over, it goes up 1. And so it must go through right there. And I can find that these two lines, these two objects intersect at the point 1, 0, which is the same thing we got right here. And so, okay, that's so, but this only works when it's easy to see, right? And that's why we didn't really develop this graphical method of doing it, because most of the time your stuff isn't this easy to graph. And even though we can graph any line, it doesn't mean that I'm going to be able to just draw two lines easily and find, oh, that it intersects at like 13/7 and 5/2. Like, that's going to be hard as hell to try to draw that out. So it helps. This way might help if it's an easy thing to graph. With lines, this way always works, but there's another way that we didn't really get into, but works with any system. And that's if we take our original thing, x plus y equals 1, and x minus y equals 1, and we get one of those variables by itself. So I'm just going to take this guy, and just like I did before, I'm just going to get the y by himself. X minus 1 equals y. I don't need the parentheses. I don't know why I'm doing that. But anyway, that's the idea. What I could do is, if I could rearrange this equation to get one of the variables all by itself, then what I could do is take this and substitute that in for that guy right there. So in other words, we have two equations. I isolate one of the variables in one of the equations, and I use that in the other equation. Then let's see what that gives me. X plus, well, now instead of y, I'm just going to write x minus 1. And so I get, okay, x minus 1 equals 1. So you see, all I've done is I've just substituted the value in for y. Now I could go ahead and say, okay, x plus x, that's the same as 2x minus 1 equals 1. How about I add 1 to both sides? Because the whole point is to try to solve. In other words, I'm looking for the values, x and y, that make both of these equations true. I take this, divide both sides by 2, and I get x equals 1. Halfway there. But what's nice about this is I already have y by itself. I don't need to, I could, if I were so inclined, I could take this, plug it back into either one of these equations. I could say, well, if x equals 1, I plug that in right there. I have x plus 1 equals 1, subtract it, or I'm sorry, plug that in for x. I would have 1 plus y equals 1, subtract 1 from both sides, I'd get 0. I could do that right here. I've already gone through the hard work by getting y by itself. Why don't I just go ahead and do that? I could say, well, since we know that x minus 1 equals y, I could just take my new thing, plug him back in, and I get 1 minus 1 equals y, or 0 equals y. And so we end up at the exact same place that we got through the other methods as well. You following this? Make perfect sense thus far? You following?
Yeah.
Yeah, okay, cool. So, okay, we didn't do this method or this method because in general, when you have lines, this way is always going to work without fail, without exception. And so we might as well just do this. With these guys, now we're talking about the intersection of conic sections. In particular, this right here is a hyperbola. This is a circle. And so it turns out that we cannot use linear algebra, or we cannot use matrices to find where these guys intersect in general. So this method is out. That is not going to help us. There are special cases of systems of conic sections where you could, but it's not going to work every single time. And it's especially not going to work in this case. You're never going to happen. And so it's like, well, since that's the case, let's just use a method that's always going to work. And what I suggest we do is a mixture of both of these methods. And so what I'm going to say is that anytime we're given a system of conic sections, or we're told to find the intersection of two conic sections, our first step is always going to be to graph those guys out. Now, this graph does not need to be perfect. And most of the time, we're not even going to label the graph at all, as you're going to see as we start doing this. It's really just as a guidepost for us. Every now and then, though, we're going to get lucky. Just like in this case, it was really lucky that I could just look at this and go, oh, wait a minute. That's this, that's that. Oh, it has to go through right there. It's obvious. I didn't need to really do any work aside from just graphing the thing. And then the answer just popped right out. Sometimes you'll get lucky with conic sections. And it's like, well, if I don't have to go through all this hard work, which is what the other part of our method is going to entail, it's like, well, if I could just get away with just graphing it, well, maybe I'll just do that. And so I think it's a good practice to adopt, because again, sometimes you get lucky. But as you'll see, it will help us to wrap our mind around what's about to happen, to have a nice visual representation. That way we'll be able to see, okay, this thing should intersect in like 4 places. And so I'm looking for 4 values here, and so on and so forth. Whereas if you don't graph it, you're just plugging things into things, and you can easily miss the big picture. So that's what we're going to do. We're going to start with this question right here. And it says, find the intersection of this thing and this thing. So I'm going to say, let's graph this thing first. This is one of those weird hyperbolas that's not in that standard form of a hyperbola. And so I'm going to solve for y. And I'm going to say, okay, this is the same thing as y equals 2 over x. I'm going to go ahead and graph that guy. And this is going to help inform me of what we're doing here. And I know since it's a positive thing, it comes down like that. It has asymptotes here and here, and like this. So basically, right, with these, there's 2 possibilities. If that number is positive, it looks like this. If that number is negative, well, it's just flipped over the x-axis. So that's where we're starting. You'll notice I'm not labeling any points on this thing, because that's not the idea of what's going on quite yet. And whenever we have a hyperbola like this, right, one of these types of hyperbolas, what we're going to do, we're going to basically assume the worst case scenario with this thing right here. So first off, what is this thing? What kind of conic section is this guy right here?
Circle.
It's a circle, right? And I guess it has a radius of square root of 6. And you'll notice I haven't labeled anything here, like I could if I wanted to. But there's basically 3 things that could happen, because he's centered here at the origin, right? That's a circle based at the origin. It hasn't been shifted right or left. And so there's 3 possibilities. Either this radius is so small that there is no intersection, right? It would just be in here. Since it's centered here, as we go out, I guess the next possibility is that it touches once here and once here. And then the next possibility is that root 3 is large enough so that it actually intersects in a bunch of places. In fact, 4 places. And my recommendation is that you assume this worst case scenario just to start off with. You might be wrong. You might have started off with this picture right here, and you go and do stuff and find, oh wait, no, I drew the wrong picture. I think maybe you come up with a better method of doing it. I just like to assume worst case scenario. And what we're going to do this one, and then we're going to do 2 more that are those special cases, and we'll see how we could identify if indeed we drew the wrong picture to begin with. Because that was the question, right? Like, is this tiny little radius? Is it big enough to touch twice? Or is it so big that we actually get 4 points of intersection? That's the question. And so what I'm expecting now is 4 unique points. And let's just take a look at this right away. Okay, like I should be expecting a point here on the x-axis, a positive one, a smaller positive one. I have a small negative one and a larger negative one. So I'm expecting something like that. I could make a symmetry argument and say, well, blah, 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 this has to be the same distance, but I'm not going to worry about that quite yet. Okay, so what we want to do is, now that we've graphed it, and we didn't get any nice information out of it, and you're really not with these hyperbolas, but now that we graphed it, I'm going to say, okay, now let's substitute. And what I'm going to do is get one of the variables by itself. Oh, I've already done that. That's nice. And I'm going to go ahead and tell you, with these hyperbolas, this is the thing you want to do almost every single time. And I can't think of a time where you wouldn't get y by itself and then just take that and plug it into this equation. I can't think of a couple times, but either way you do it, you might end up doing one extra step doing it this way than you would by doing it another way. So I'm going to go ahead and recommend with hyperbolas like this, xy equals some constant. Get the y by itself, take that and plug it in to your other equation. So first I'm going to write the other equation right here. You'll notice this is exactly what I did a second ago with those lines, right? I had 2 lines. I took one of them and got y all by itself. And then I took that expression and plugged it into the other equation. That's what I'm doing here. I took one of these. I got y all by itself. Now I'm going to take this value and plug him in for y. And let's see what happens. It says we take y squared. And so I'm just going to plug it in. Y, that says, is 2 over x. Okay, so now I have x squared plus, let's go ahead and square that out. 2 over x squared is the same thing as 2 over x times 2 over x. So that should be 2 times 2 is a 4. X times x is x squared. And so we have 4 over x squared equals 6. Almost like a polynomial. The only problem is I have a denominator. A denominator is messing up my life right now. So what do I want to do to get rid of that denominator?
Multiply each side by x squared.
There we go, right? Because I'm just looking at this and going, whoa, that's not nice. I don't like him. I could kill him by multiplying by x squared. So I got to do that to everybody. And so when I do that, I'm just going to be explicit here. And I'm going to say, okay, what I'm doing is I'm taking this equation and both sides, I'm going to multiply by x squared. So the x squared distributes over and gives me a total of 4 x's, or x to the 4th. X squared comes over here, kills that. It's the whole reason I chose x squared in the first place, was to kill that one denominator. And now I have 6 times x squared is 6x squared. Now I have a polynomial. And it's in terms of x. And I know I'm not really, again, I'm not using my brain. I just know, like, hey, polynomials, I can solve polynomials if I make them equal to 0. And so why don't we get everybody on one side of this thing? And we're going to go, okay, that's x to the 4th minus 6x squared plus 4 equals 0. But the problem is, what do we do with something to the 4th power? You remember what to do with this? We talked about it briefly. You didn't have any homework over it, but we talked about it. And I recommended that you look over this section. Notice that this is off by, and this is kind of the question when we have something like this, we ask ourselves, can I take this thing and square it to give me the higher order term right here? It turns out we can, because x squared is x to the fourth, right? Let's just be really clear about that. If I took x squared, took it and squared it, I would have, well, x squared times x squared. I would have a total of 4 x's. I would have x to the fourth. And so we could say, aha, okay. I could make a substitution. And I'm going to say, okay, well, then the substitution I want to make is I'm going to I could call it anything I want. I'm going to say u. I'm going to say let u equal the smaller thing. So that when I square it, I get u squared is equal to, well, x squared we just saw was x to the fourth. And now I could say, aha, instead of writing x squared here, I could write a u, and instead of writing x to the fourth there, I could write u squared. And now I have a quadratic, and there is no quadratic in the world that we cannot solve. We could solve every single quadratic. And so that's the idea, right? Like we have something that's certainly not a quadratic. That's something to the fourth power, but we say that this has quadratic form. That means that we could do a nifty little substitution like that to turn my hard problem into a problem that I've seen before, which is a quadratic. So now, okay, what do we want to do? Well, could try to factor it, but I could tell you this ain't going to factor because it's either a 1 and a 4. 1 and a 4 aren't going to give me a 6, or a 2 and a 2, and 2 and a 2 aren't going to give me a 6. And so I think I'm going to use my best friend, the quadratic formula. In this case, I'm just going to go ahead and write them out and say, okay, then u equals, because it's not x equals, right? It's u. That's the variable we're solving for. U equals negative b over 2a. So negative 6 would be positive 6 over 2 times a is 1 right there, 2. Plus or minus the square root of b squared, right? So 6 squared is 36. Minus 4 times a times c. So 4 times a is 1 times c is positive 4. So that's 4 times 1 times 4 is 16. Looks like. So minus 4ac is the same as minus 16 all over 2a. 2a is 2 times 1, and so it's just 2 right there. Okay, not bad. See if we can reduce this a little bit. 36 minus 16. It should be 20. Yeah, it should be 20. Okay, so I'm going to go ahead. So I'm going to kind of simplify as we go on. 6 over 2 is 3. Plus or minus. Now we just said that's the same as square root of 20 over 2. And I mean, technically, we could stop here. We could have stopped right there. That's fine. It'll be easier for us in a minute just with notation if we go ahead and reduce this guy a little bit further. So just to be clear, I'm not saying that we have to, like if we wanted to just stop there and go back and find what x is and all that, we could. It will be easier for us if we go ahead and reduce him. So I'm going to say, okay, square root of 20 is the same thing as the square root of 4 times 5. Oops. Square root of 4, that's easy. That comes out as 2. Square root of 5 does not reduce. And so we have 2 root 5 like that. So we have u equals 3 plus or minus 2 root 5 over 2. And this is what I meant. Like it'll make it slightly easier to see if we go ahead and reduce this down. So we finally get u equals 3 plus or minus the square root of 5. Okay, almost done. So I'm going to get rid of this stuff right here. And now at this point you go, oh, okay, 3 plus or minus square root of 5. Wait a second. This is u. This is not x. We're talking about x and y over here. This was a fake variable that I made up. U does not exist. And so what I have to do now, and we can do this a few different ways, I'm going to do this explicitly here and say u is either equal to 3 plus the square root of 5, or u is equal to 3 minus the square root of 5. Now I'm going to substitute this guy back. I'm going to say, wait a second, but we don't care about u. U isn't the variable we were after. We were after x. So I'm going to say, okay, x squared is equal to 3 plus square root of 5, or x squared is equal to 3 minus square root of 5. Now, how do I solve for x? Okay.
Sorry, I'm just catching up.
Okay.
Take the square root of each side.
Take the square root of both sides, right? And when we do that, we get a plus and a minus. But hold up. This one we could totally take a square root of. 3 is a positive number, plus square root 5, positive number. And square root 5 is about 2 point something. I'm going to be a little pedantic. How do I know that? Just this may or may not be helpful, but here's the idea. I'm trying to get a bound on 5, or on the square root of 5. So I'm going to look at 5, and I'm going to look for the nearest perfect squares to 5. The nearest one on the left-hand side is 4. The nearest one on the right-hand side is 9. See what I mean by that? Like the nearest ones to it, like 4, 5. Yeah, okay. 5, 6 is not a perfect square. 7 is not a perfect square. 8 is not a perfect, but 9 is. And so I could think about it like that and go, okay, then the square root of 4 is less than the square root of 5, which is less than the square root of 9. And so 2 is less than root 5, which is less than 3. So I could think about 5 square root of 5 as 2 point something. Not sure what, but it's 2 point something. So I could say 3 plus 2 point something is 5 point something. So it's a positive number. No problem there. 3 minus 2 point something. Well, it's still positive, right? Because 3 minus 2 point something, who cares, whatever, is still a positive number. So we do need to check that, because like I said at the very beginning, I'm expecting 4x values here. But I'm not sure if I drew my picture right. It might have been the case that this only touched in 2 places. It might have been the case that this thing was a tiny little circle and there actually was no intersection. So this is something I really need to consider here. Like, it might be the case, like, if this came out to be x squared equals -1 and x squared equals -7, I'd know, uh-oh, wait a second. I'm going to take a square root and I'm going to get imaginary numbers. That means that there actually wasn't an intersection here. I'm looking at this and saying, okay, that's a positive number. I could take the square root of it. If this happened to be negative, then that would tell me, oh, wait a second, I'm only going to get 2 values for x. My original picture must be messed up somehow. But I've done this little bit of work and said, wait, hold up. Square root of 5 is 2 point something. So that's a positive number. Okay, so I could take the square root of it and I end up with plus or minus square root of 3 plus square root 5. Or, and now I say, okay, I could take the square root of this stuff. And since it's positive, I could do that. No problem. I do get real values. 3 square root of 3 minus square root 5. we are almost done. Now, the thing is, I'm just thinking about what's going on now. At the beginning, I anticipated 4 unique points of intersection, which means I should have 1, 2, 3, 4 x values, 4 unique x values that come out of here. That's what I'm seeing, right? These are different numbers. That's 3 plus 2 point something. So 5 point something. I take the square root of that. And then I have a plus or minus. I have 3 minus 2 point something. And so I have point something. Take the square root of that. And I have a plus and minus. Okay. Things are looking pretty good. So, all right. Go ahead and do that. Can I get rid of this work right here?
Just 1 second.
Okay.
Yeah.
Okay. So now what I want to do is kind of put this all back together and say, all right, I want to find where these points are. And we already know, we've already talked about this. This is the bigger one of these things. And so the positive bigger one has to be this guy who's the farthest to the right on the x-axis. It's kind of hard to see when you have square roots inside square roots, but just imagine you had like square root 17 plus or minus and say square root 6 plus or minus. You'd say, well, the 17 is the bigger one of all of these. That's got to be the biggest one. So he's got to be the furthest right here. That would have to be square root 17. And could then argue, well, then the negative one has to be the furthest to the negative, which would be that guy there. And then the smaller ones would have to be, the positive one would be this guy right here. And the negative one would be closer to the origin. He would be on that side there. So that's what we're going to do here. And what I'm going to do, this is one of the few times I'm going to recommend this. Let's just label all of these as points. Because if we try to put all of the x values right here on the x-axis and then all the y values, it's just going to look terrible. So what I'm going to do now is, finally, I'm going to finish up my graph. I'm going to say, okay, I'm going to label this as a point. That x value has to be the biggest positive one, and that's the biggest one. And so the positive one must be square root of 3 plus square root 5 right there. So that's that point, 3 plus root 5. Don't know the y value yet, but we'll get there in a second. I'll leave a little space for that. Okay, and I could just go down the line. That would be fine. I could say, well, then the smaller positive one has to be the next one over. And that would be that guy right there. It's a positive value, and I'm going to take the positive one. So that has to be the positive square root 3 minus square root 5. I could have, I think it's easier to do the big values first. We say that's the big one. The positive one must be over here. The negative one must be over here. That's probably how I would have done it. I would have just gone for the big ones first and say, okay, that negative big value has to be the farthest left. And so he's going to show up down here as negative 3 plus root 5 square root. It looks terrible. I'm running out of room. And then, well, there's only one left. He's the smaller in absolute value. 3 minus root 5 is point something. Square root of that small. And then the negative one is going to be this guy right here because he's closer to the origin. Makes sense. And so negative square root 3 minus square root 5. Any questions on how I figured out the order of these guys? Is this all making sense? Why The plus one shows up here, the minus, and the plus, and all that.
I think so.
And really, all I'm doing here, I'm really reasoning by analogy. I'm just saying, well, hold up. Just same way I would do with this. Like, which one of inside the root, which is the bigger number? Well, like if it were just 17 and 6, I'd say, well, the 17 is the bigger number. And so that has to be the farthest over here in the x direction. That guy has to be right there. The negative of that would have to be the farthest down there. The smaller of these 6 is not going to be as far away from the origin, so he would have to be that guy right there. And so on and so forth with the positive and the negative. And so now that I've labeled these, well, half of these 4 points, I could just double check it and see, like, okay, the x's over here are both positive numbers. Yeah, I'm good. The x's over here are both negative numbers. Yeah, we're good. In absolute value, right, that is a bigger number than that. And so, yeah, of course, he's over here. And then, yeah, same thing down there. It's just negative. And so, okay, that looks good. The last thing we need to do is just find the y values for each of these guys. And like I said, with my when I did that original substitution problem with the lines, I could take my final answer, which was x equals 1, and I could plug that back into either of these equations. And I would find that in our original case that y equals 0, no matter how you chose to go about doing it. And so I have 2 equations to choose from. I could take each one of these values, plug it in for x into, say, this equation, and then go and solve for y. Or look at that, I already have y by itself. And so why don't we just use that guy instead? Because, well, these are points that are on both of them. I could use the circle to find it, or I could use the hyperbola to find it. And that is really nice. It's kind of like earlier when I already had y equals minus x plus 1 or whatever it was that I had. And I said, we could plug it in or whatever, but this one's already there. All you got to do is plug that guy in and hey, it gives you your answer. Same kind of thing here. You could say, well, I already have it. I could just plug it in. And that's what I'm going to do. And I'm not going to try to simplify this or anything. I'm just going to say, well, in this case, when x equals square root of 3 plus square root of 5, then y equals 2 over x is what I get when I just plug that guy in for x. And so in this case, real easy. I'm just going to take 2 over whatever that number is. I'm going to say that the height of this is 2 over square root of 3 plus square root of 5. Same thing here. Don't need to use my brain. How high up is it? Well, you just take 2 over that amount right there. And so this guy would be 2 over square root 3 minus square root 5. Same object, we're still on the hyperbola here. And so it's the same formula to find the y value. I just take 2 over whatever this x value is. In this case, the x value happens to be negative, so that's cool. 2 over negative square root of 3 minus square root of 5. Finally, that last one, it's gonna look really ugly because I'm running out of space here, but it is 2 over the negative square root of 3 plus square root 5, like that. Those are my 4 points. So it turned out in the very beginning I said, all right, let's just draw a hyperbola. I'm not going to worry about making it to scale or worry about anything like that. Now I got to intersect it with a circle at the origin. Well, let's assume the worst case scenario. Like we assume that it's going to hit in all 4 points. And indeed, then we substituted something in and found, oh, I have 4 X values. So, yep, that's going to give me 4 unique points. And then we just did that. The whole time I'm using my picture to kind of guide me to, to make sure like, yeah, this jives with the picture. One of these is big, one of them small, one of them's negative, one of them's even more negative. And now, finally, just to kind of check myself, I'm going to make sure that all of this works. Like 3 plus root 5 is the bigger X value, so he's far to the right. And then I take 2 over something bigger is further down than 2 over something smaller. What I'm thinking about here is, and that's exactly what this line means, right? Like, on one hand, if you have 2 over X and you plug in a 1, you get out a 2. If you have 2 over X and you plug in a 4, a bigger number, you have 2 over 4, which is 1/2. It's a smaller number, right? And so, yeah, plug in a bigger number and it goes down more. That's what I'm seeing in both cases. So that looks good. That the 2 divided by the big number is further down. 2 divided by the smaller number is higher up. Looks good. Same thing over here. 2 divided by a big number is a smaller, so it's closer to the x-axis, and it is a negative number. And so down here we have a negative and a negative, which we should have. Down here we also have a negative and a negative. That's what it should be. And okay, so that's it. That's what, so you're going to have in your homework 1, 2, 3, 4, 5, 6, 7 of these questions. And for each one, this is what I want. A picture labeled with the points of intersection, just like this. But now let's talk about what happens if you screwed up your picture. What if you drew the wrong picture to begin with? That's what we're gonna do right now. Can I get rid of this example?
Yeah.
Okay, so almost the exact same question. Almost exactly the same. Here's the difference. Find the intersection of xy equals 2 and x squared plus y squared equals 4. And again, like I'm going to say, okay, start with this guy, because just trust me, start with, when you have a hyperbola like this, start with that. And so I'm going to draw my x. And I'm going to say, okay, y equals 2 over x looks like this, and I draw like this, and I draw like this. Now I could get hung up right here and say, well, wait a second. The square, that's the square root of 4 is 2. So that's a circle with radius 2. Oh, wait, but if I plug in a 1, I get out of 2. Is that, oh, how big is it? What should it do? What did I say? Assume the worst case scenario. This is how we're going to start. We're going to assume that this thing intersects in 4 places. We might be wrong. And that's why I'm not taking much of any time to draw this. I'm just going to thumbnail sketch. That's a commonly used term. Like I didn't put any energy into this. It's just a thumbnail sketch. It's just, we're just going to use it. Maybe it's wrong. I'll scratch it out. No big deal. But I'm going to use the same exact method to solve this. I'm going to say, okay, I already have this guy, one variable all by itself. So I'm going to take this variable, plug it into the other equation, x squared plus y squared equals 4. And so x squared plus stuff squared equals 4. The stuff I'm plugging in is, instead of y, I'm going to have 2 over x. That gives me x squared plus 4 over x squared equals 4. same thing as last time. And all of these that you're going to have with the hyperbola and some other kind of conic section, you're going to end up with one of these types of equations where you have an x squared or a y squared in the denominator, so that you have to multiply everybody through and you get something like this. And then you're going to pull him over to this side. And you go, wait a second. Yeah, if I take that and square it, I get that. So this is a quadratic form. It's just, we just need to write it as a quadratic. And so I'm going to do the same trick as before. I'm going to say let u equal x squared, so that u squared equals x to the fourth. And substitute that guy in and say, okay, u squared minus 4u plus 4 equals 0. I try to factor it. That ain't going to happen. Actually, it will, but no, will it? 2 and a 1? No, that ain't going to happen. And so, oh no, what do I do? Well, let's see. How about we just again use the quadratic formula? Are you up to here yet? Can I go ahead and plug along with that quadratic formula?
One second. Please.
Okay.
One. Zero. U equals squared. All right, we're good.
Okay, so I'm going to say, all right, now x equals negative b plus or minus square. Okay, so u equals negative b over 2a. So negative 4 is 4 over 2a is 1, so 4 over 2 plus or minus the square root of b squared. So that's minus 4 squared is 16 minus 4 times a is 1 times c is positive 4, comes out to 4 times 1 times 4 is positive 16. Oh, uh-oh. All over 2a. It's actually nice. This will actually help us out, because we could say, wait a second. 16 minus 16 is 0. The square root of 0 is 0. So the square root of 0 over 2 is just a big fat 0. And so I get u equals 4 over 2. Or in other words, u equals 2. And we could say plus or minus 0, but that's not the point, right? So yeah, u is equal to 2. And just 2. There's no minus 2 there. It's just 2. So, okay, we have one solution with u. And so I go, okay, u equals, oh wait, we don't care about u, we care about x. So same thing as we did before. We're going to say, okay, u squared, or u equals 2. But u is actually x squared. We just rewrote it to help us out. So now I can take a square root of both sides, and I get that x is equal to plus or minus square root of 2, just like that. Now we look back at our picture and go, okay, I have two answers. Either x is equal to minus root 2, or x is equal to positive root 2. And I look back at my picture and go, oh, whoa, I must have drawn that messed up, because here I'm ending up with only 2 points of intersection. This says we have 4 points of intersection. Oh, okay. So I know that I must have screwed up my original picture. I'm going to forget about that. The only other options, right, like we discussed at the beginning, is we're starting off with, in fact, I'm just going to go ahead and erase this to give myself some room. And say, okay, from the beginning, this thing looks like this. My only options were, since that's centered at 0, either it's too small to hit it's so big that it hits in 4 places, or the only other option is that it touches in 2 places, right there and there. Now I can see where those places must be. It must be here at x equals positive root 2 and negative root 2. And what I'm going to do is label these as points in the plane. I'm going to say, okay. Well, the plus root 2 must be on the right-hand side, so that's easy, square root 2. The minus root 2 must be on the left-hand side, so minus root 2 right there. And then to find the y values for that, I just plug it back in. If I were so inclined, like I said before, I could plug it into this one. And let's just to drive the point home, let's do that with one of these. If I took x and plugged it in right here for this right here, I could say, okay, x is equal to square root of 2. I would have this right here. Square root of 2 squared is 2 plus y squared equals 4. Subtract 2 from both sides. I would have y squared equals 2. Take the square root of both sides, and I'd have y equals plus or minus square root 2. And I could see, aha, it must be the plus one right there. It must be plus square root 2. Or you could make it really easy on yourself and just say, well, why don't I just plug that into there? So you go, in other words, y equals 2 over the square root of 2. And you could just write it like that if you're so inclined. You might say, but wait a minute, Justin. Like you just said that we get the same thing here, and it looks like 2 different things here. How could that be? Well, this reduces, doesn't it? In fact, 2 is the same thing as the square root of 2 times the square root of 2. Which cancels. And so we could say, then this is just equal to the square root of 2. Do you want to write it as 2 over square root 2? I don't care. Another way of seeing this is we could say, well, hold up. 2 over square root 2, I could multiply the top and the bottom by the same number. There, and I get 2 root 2 over square root of 2 times square root of 2 is just 2. And so, oh yeah, it just comes out to root 2. So no matter how you look at it, this is good. If you wanted to write it as just 2 over square root 2, that's fine. That's cool too. The last one, I'm going to do the same trick. 2 divided by whatever that is, right? Because I'm just plugging it into here. And we could say, okay, 2 over negative square root 2 gives me negative square root 2. Or if I wanted to, I didn't need to reduce it. I could just write it like this. I could just say 2 over negative square root 2 and just plug it in right there. Fine. And so, okay, stepping back, what did we do? We said find the intersection of 2 things. I started off by drawing the wrong picture. I said, okay, we have a hyperbola and that looks like this. And we'll assume that this radius is big enough to intersect at 4 places. I did my stuff and found, oh, it's only intersecting at 2 places. So I said, okay, well, I drew the wrong picture, scribbled out my picture, did a thumbnail sketch, which took me 2 seconds. And now I can see, okay, it must be the case that this is exactly just touches right there at 1 place. I'm sorry, 2 places, here and here. And labeled my points by taking the x values I found and plugging them back into the y, which also would have worked if I used the other equation, but why make your life harder than it needs to be when you could just, you already have it solved for y, so just use that. That's the idea. Any questions with this guy right here?
No, actually.
Cool. Okay, so one last case of this type of system that I want to look at. So the last thing would be something like this. Find the intersection of, or in other words, solve. They just give you 2 equations and say solve. In other words, solve the system. And they give you, one of these guys and something else. And so we go, okay, let's draw that guy first. So we solve for y, we get y equals 2 over x, and we draw it. And we go, okay. this. All right, that's what that guy looks like. And now we say, okay, that is a circle centered at the origin, has radius square root 2. And so, well, Justin told me to do this. So I'm going to do that. I might be wrong. It's all right if I'm wrong, but I'm looking for 4 points of intersection. All right, so same thing. We're not changing anything here. We're going to say, okay, I have one equation, solve for one variable. And so let me take that and plug it into the other equation, giving me just right here. I'm going to take y and write that as 2 over x, which gives me x squared plus 4 over x squared equals 2. Kill that denominator, multiply everybody through by x squared, giving me x to the 4 plus 4 equals 2x squared. Yep, we have a polynomial. Let's get that polynomial equal to 0. So I do that. X to the 4 minus 2x squared plus 4 equals 0. Uh-oh. Something to the 4th power, something squared. Oh, something squared, something to the 4th power. I could go u equals x squared, so that u squared is equal to x to the 4th, and I can do a cool substitution. So that's what I'm going to do. I'm going to say this is the same thing as u squared minus 2u plus 4 equals 0. Yeah, okay, that all looks good. And now I'm going to say, can I factor this? 4 and 1, 3. No, not going to happen. 2 and 2. 2 and 2 can't give me a 2. Looks like I'm going to have to use the quadratic formula. And so I get u equals negative b. So negative 2 is positive 2 over 2a. A is 1, so that's just 2 plus or minus square root of negative 2 squared is 4. So b squared minus 4ac. So 4 times a times c. That's 4 times 1 times positive 4 is again 16. It's been 16 every time. Funny. Okay, so minus 16 divided by 2a. A is 1, so 2 times 1 is that. So 4 minus 16. I'm going to clean this up a little bit. U equals 2, which is 1 plus or minus. Okay. 4 minus 16 is minus 12, I think. Yeah. And I take the square root of that. Taking the square root of a negative number gives me an imaginary number. So that's I times square root of 12 over 2. And now here we go. What this is telling me, and we can't prove this in this class, but it's true that you might wonder, well, hey, just because that's imaginary, I know what I'm about to do. I'm about to take that number and say, wait a minute, it's not u equals that, it's x squared equals that. And so is it possible to take, if I take the square root of an imaginary number, can I make the imaginary part go away? Can I get something pure real? It turns out, no, you cannot. We can't really, it's not too hard, but we can't really prove that in this class. It turns out that the square root of something that has a non-zero imaginary part will always give you an imaginary part. And so right now we are done. We could say, wait a second. In this case, we get u equals this, which means that x squared has an imaginary part, which means that x has an imaginary part, which means it's not pure real. So rather, x isn't a pure real number. Which means that in this context, these points don't exist. So what must be the case? Oh, the only way that this could have been is that I drew the wrong picture to begin with. This thing should have been something like this, and our circle is too small to intersect the whole thing. So that's what's going on. And indeed, like we saw that last time, right? Like the distance from here to here, back when we had our circle that touched only at one point, right? That circle, that was when x squared plus y squared equals 4, or in other words, x squared plus y squared equals 2 squared. So that radius must have been 2. This radius is even smaller. This radius is the square root of 2. So it's even smaller. It can't touch that. And if it were easy to get a handle on these things and say, well, I could just tell that that's smaller than that, I don't really have a feel for that. Like, if you ask me, is the square root of 2 long enough to touch one of these? I have a hard time with that. And if we were in calculus, we would prove a way of figuring that out. But without a proof, I'm not going to tell you the secret because I don't like to do that. Like, there is a way of just figuring out how far that the smallest distance is between here and here. But my point is, these things, we don't really have a good feel for these things, especially in relation to other things. So we're going to just start by assuming the worst case scenario. We're going to assume that these things intersect in 4 places. And then when something like this pops up, we'll go, oh, wait a minute. It must have been the case that my original picture was off. This thing must be smaller somehow. It doesn't touch at all or something like that. So that's my spiel on how to deal with these types of intersections where you have this type of hyperbola. And this could have been an ellipse. It could have been another type of hyperbola. It could have been a circle, which it was. And the thing is, the method's going to be exactly the same. Start with this ugly hyperbola and then draw your stuff, and so on and so forth. So any questions with this stuff?
I don't think so.
Okay, it should be pretty straightforward. And now what we want to do, just briefly, we want to discuss a couple other things, because you have a bunch of these. You have like 4 with this type of thing, but we want to go over other types of intersections of things. So one that I want to discuss is this. We're going to say, find the intersection of, let's go, x squared over 2 squared plus y squared over 3 squared equals 1. And x squared over 2 squared minus y squared over 5 squared equals 1. Okay, so we're given 2 things. Now, in your homework, they're not going to be given like this to start off with, right? I went ahead and did the work here to get it into a form that's going to be easy to graph. And so, okay, first step, graph it. Okay, so this is, what is this? This one right here. And let me know when you have this written down. Let me just kind of take a break for a second. So did you finish copying this down?
Sorry, I was on mute. Yes, I'm done.
Okay, so all right, what type of thing is this first one right here?
That's a hyperbola. No.
Nope.
Oh right, mine is a plus. Gosh.
Couldn't hear you if you said something.
What?
I couldn't hear if you said something.
Oh, that's an ellipse, right?
It's an ellipse, okay? And so, and this one is what?
A hyperbola.
Hyperbola, okay? So I'm just going to draw them. And again, I'm not going to make a big fuss about this, but it may or may not help me to do this one accurately. So let me just do this. So I'm going to say, well, and these are easy because I already wrote them like this. There's 2 and a 3. Okay, so it goes in the x direction. It goes through at plus and minus 2. So I'm going to go ahead and do that. And then it goes in the y direction at plus and minus 3. And so it looks like this. Okay. Now, again, I'm not too concerned about finding the correct things. I mean, like, we don't need to label all this, but watch what's about to happen. Okay, does this ellipse go through the x-axis or does it go through the y-axis? I mean, ellipse.
Say that again.
Does this hyperbola go? Yeah, you see, I'm doing it too. No shame in that. Does it go through the x-axis or does it go through the y-axis?
Let's see. It goes through the x-axis?
Yes. Where?
At -2 and -2.
There you go. Right, because forget about this. We're imagining if you're on the x-axis, your y is 0. That happens to make this entire thing go to 0. Bring the 2 up. X squared equals 2 squared. Then x equals plus or minus 2. So I can draw this guy here at plus or minus 2 goes like that. And oh boy, look at that. I found the intersection. I don't need to do any more work. Okay. Like I'm certain that this is what that thing looks like. And if I were so inclined, I could find the asymptotes as well. But that's not the point of this. It just says find the intersection of these 2 objects. And I have. I graphed it and it happened to be, this is kind of like the very first thing we did with the lines. I happen to have really easy lines that happen to intersect in a really easy place. So I could have just stopped there and said, that's where it intersects. And so that's what I'm going to do here. I started off with the picture and it happened to be the case. Okay, I have these 2 points and I'm just going to go ahead and label them. Here's one at 2, 0. Here's one at -2, 0. And hey, my hard work paid off. I don't need to do any kind of substitution or anything like that. So in that case, hey, life was good. So finally, the last one of these types of things we're going to do is find the intersection of this thing and that thing, which is x squared minus y squared over 5 squared. What do you do? Want to do 5 squared? Yeah, it'll be fine. Okay, so we'll do that. So let's say we have that. Now in your homework, it's actually not going to be given that way. Like I said, I went ahead and did the work of bringing these guys down into the denominator and all that stuff. We are actually going to be given is, well, if I went and multiplied this through, this original thing would have been 9x squared plus 4y squared equals 9 times 4, I guess, is 36. This thing would have been given as 25x squared minus y squared equals 25. That's how these two things would have been given to you. And you'd say, well, hold up, that's an ellipse, and we go and do that and then graph it. And you'd say, okay, what's this other thing? I guess it's a hyperbola, and we'd go and do this, and then we go to graph it. So you following? I already got the first part here. I turned my original thing into this thing and said, all right, I'm going to graph it, which I already did. We identified A. That's an ellipse. It goes through it, plus or minus 2, plus or minus 3. All right. And then this thing was given like this. And I said, well, hold up. If I get this thing equal to 1, then okay. And I did that, and it gave me that. And I could say, okay, this is a hyperbola. And again, does it go through the x-axis or does it go through the y-axis?
Wait, which one?
The hyperbola. Does it go through the x-axis or the y-axis?
Goes through the x-axis?
Yes. Where?
1 and -1.
Yes, there we go. Right. And it's easy to see in this form right here, because we could say, well, when y equals 0, you have x squared equals 1. And so plus or minus 1. You know, I mean, or I wouldn't recommend trying to do it this way, but it means the exact same thing. You'd have a 0 here. You'd have 25 and 20. Oh, I'd divide both sides by 25 and have 1. And take a square root of both sides plus or minus 1. That's why we have this nice form, because you could just see it. And so, okay. So it goes through it plus and minus 1. And so, ooh, that's going to be in here. Plus 1 and minus 1. And so it must look like this. And again, I'm at this point, I'm not concerned about asymptotes or anything like that. Because again, the only reason I even bothered labeling points is because, well, this kind of lends itself to it. Like in the first 3 examples we did, I never labeled any points, like as I was sketching it, because it wasn't going to help me. This might help me, because like we saw in the very first example of these that we did, hey, they happen to intersect like really easily. And so, hey, my graph took care of it. So in this case, yeah, I take a little bit more care to draw this stuff out. And now I can see, oh boy, I'm expecting 4 points of intersection. This thing should go here, and here, and here, and here. And I have drawn that terribly. One thing to note, why I'm going to not really making a fuss. Thing to note is that these things are symmetric, right? And so what I'm expecting from this symmetric looking picture is that these 2 points occur at the same x value. And if I had drawn this really well, it would be easy to see. Like if I had my ellipse like that, and I had my hyperbola that was exactly symmetric across there, we'd be able to see pretty easily that those 2 points would have to have the same x value. I can't draw, save my life, so it doesn't really look like that, but that is going to be the case with these types. And you'll have plenty of examples that are like this. And so I'm expecting 4 points of intersection. So what I'm going to do now, and I have my choice, and you can imagine if like these numbers had been mixed around in different ways, that I might want to solve for something like, for instance, in this case, and you'll notice we're going to use these two equations. If we were so inclined, we could use these two equations to solve our stuff, but it's going to be easier to do it this way. And you'll see in just a second. So I could choose either one of these to get one of these by itself. And this really looks like it's just begging me like, hey, that y is almost all by himself. It'll be really easy to get that y by himself. In fact, that's the way I'm going to go with this one. I'm going to say, okay, then, how about 25x squared? I'll bring the 25 over to this side. Minus 25 is equal to y squared. And at this point, because you're kind of on autopilot, you're going to say, okay, now take the square root of both sides. And you could, if you wanted to. A couple things to note, though, is like, I'm about to plug this into here. And this thing, y squared, whatever it is, it tells me is that thing. And so I could take that thing and just replace it with y squared. That's, in fact, the way I'm going to do it. Just to show you what I'm talking about here is, let's say you were just on autopilot and you said, okay, then this is equal to plus or minus 25x squared minus 25. And so you go and plug that into this equation and you'd have 9x squared plus 4y squared equals 36. And you'd plug that into here and you'd go, okay, that's plus or minus, it doesn't matter, 25x squared minus 25. And then you'd take that thing in a square root and you would square it. Oh, I didn't need to do that in the first place, did I? Because if I took it and squared it, I'd be left with whatever's inside of it. Square a square root, it just comes out to be 25x squared minus 25, which is what we would have had if we had just stopped and said, wait a second, wait, that symbol, y with a little 2 up above it, means this. And I could just take that and replace him where I see that symbol, and oh, lo and behold, we would have the same thing. So if you're on autopilot and you do get the y all by himself, well then, okay, cool. It'll work. You'll just have to do 2 extra steps. Or you could stop and go, well, wait, hold up. That means that. And so I'm just going to plug them in. So that's what I'm going to do. I'm going to say, well, hold up. This is that. And I'm going to take that and plug it in here. 9x squared plus 4 times that stuff equals 36. That stuff is 25x squared minus 25. This looks like it's going to be terrible, right? But actually, check this out. It's really not that bad. I'll show you in just a second. I'm going to get rid of this, and just to really drive the point home, if you did this, you would have ended up with the same thing as that. So that's just something to note. But anyway, okay, so we get one of the variables by itself. We take that thing and substitute it into the other equation. And then we're going to say, okay, well, I'm going to kind of go on autopilot mode here. 4 times 25 is 100. Yeah, I think. 4 times 25 again is 100, so minus 100. 36. Now this is the cool thing. X squared. Oh, I could add those together and I get 109 x squareds. How about I take that 100 over to the other side and I get, I guess, 136. Let me know when you're at this point and that you believe it. Like, double check me. I might easily have messed something up here. Just double check that you get the same thing at this point.
Yes.
Okay. So I'm going to say, okay, now divide both sides by 109. And I get x squared is equal to 136 over 109. Okay. And now I guess I'll take a square root. I could, if I wanted to, I could see they're both divisible by 3. I could try to reduce this, but I don't care. I could plug this into a calculator if I really wanted to know where it was. So I'm going to say, okay, x is equal to plus or minus the square root of 136 over 109, just like that. Now, okay, what's that going to do? Well, real quick, I'm just going to kind of double check here. Like this says that x is plus something and then minus something. In fact, it's the same distance away from 0. Hey, that's what we should, that's my picture is telling me that that's what I should have. I should have some number between 1 and 2 over here. And I should have another number between -1 and -2 over here for my x values. So that's looking pretty good. I feel pretty confident about that because I can tell that's bigger than 1, right? 136 over 109 is bigger than 1. Take the square root of it, bigger than 1. If I really wanted to, I could double check that it's also, it's like, I could, if I were so inclined, check that 136, 109 is indeed between these guys, like my picture says it is. Just square everybody out. 1 less than 136, 109 less than 4, right? Just square, square, square. You get 1, that, and that. And we can see, yeah, that's definitely bigger than 1 because the numerator is bigger than the denominator. And if you wanted to, you could double check that side too and say, well, 136 is indeed less than 4 times 109. So yeah, okay, I feel good. This number should be between 1 and 2. Nice. It's not necessary that we do this. It's just, it's nice. I like to check myself as I go along. So I'm feeling really confident about my picture here. I should probably write these 2's on the outside so that it's not confusing. There's a positive 2 out here. -2. Okay, so the only thing that's left to do is to plug this guy into, I guess, this equation. Since we already have y squared, right? I could plug him in for x, and I don't care how ugly this looks. In fact, what I'm going to do for this one, I'm not going to bother to reduce it. I'm just going to say, okay, if x, and let's go ahead and get our x's. Because again, I would like to see all of these points on here labeled. So I'm going to do that. Here are my 4 points that I'm trying to label. Okay, so the positive x's are that one and that one. And so it must be plus root 136 over 109. Right there. Root 136 over 109. And then the negative ones, the ones that are on the left-hand side of the y-axis, must be the negative ones. Negative root 136 over 109. Negative root 136 over 109. Negative root 136 over 109. So those are, so we got all of our x's labeled. The only thing that's left is to find the y values for these. So get rid of this. And hey, we have y almost by himself. We have y squared, so that's nice. I'm going to say, okay, 25 instead of x squared, I will have that root stuff squared. And so that's square root of 136 over 109. Doesn't matter whether or not I plug in a positive or a negative because I'm going to square it. And so it's going to come out to 25 times 136 over 109 minus, sorry, that minus 25 equals y squared. Now, I could pull out a 25. I don't care. Like at this point, we're almost done. I'm just going to say take a square root of both sides. And that gives you square root plus or minus the square root of 25 times this ugly number, which you can reduce if you want. And minus that. And so again, now we could figure, okay, well then the plus ones must be the ones that are up above the y-axis. And so I'm going to write those up here. That's 25, the fraction minus 25. I'm just not going to write it out. You're not going to be able to read it anyway, because I'm trying to cram this into a tiny little bit. But that's what I'm doing. I'm just taking this thing that I have, whatever it is, and plugging it in right here. That's root 25 times that stuff minus 25. Like I said, I could, if I wanted to, reduce this by pulling out a 25, and we'd have that ugly 136 over 109 minus 1 like that. All right, I could take that factor out of 25, and then I'd have 5 times the square root of 136 over 109 minus 1, which I guess I could write as something 109 over 109 and really try to reduce that down. If you're so inclined, I don't care. I mean, if you want to check your answers in the back of the book, it might be a good idea. But this is fine. I'm just going to leave it like that. So we got the positive ones up there. Now let's do the negative ones. Those must occur at that negative value. And if I had drawn this right, I would really feel convinced about that both of those would have to occur right here, because again, of symmetry, everything would come out, be nice and symmetrical. But that's going to be the minus root 25 times the stuff minus 25, like that. And that one's going to be the minus root 25 times stuff minus 25, just like that. Last step, double check my picture. I'm going to say, okay, this point right here should be positive, positive, and it is a positive, positive. This one over here should be x is positive, y is negative, x is positive, y is negative. Yep. This one over here should be x is negative, y is positive. Yep, x is negative, y is positive. Down here, we should have a negative x and a negative y, and it says that my x is negative, my y is negative. Okay, it feels pretty good. And so these, where you're doing the intersections of two conic sections, and one of them is not in this form, the crazy, the crazy xy hyperbola, they actually turn out to be easier as far as I'm concerned. Like, it reduces down to one variable that's squared, and then you take the square root and you end up with something like this. I don't think you have any that have been crazy shifted around or anything like that. They're all really straightforward systems like this, where everything is just either an ellipse or a hyperbola or a circle that is centered at the origin. You have a few that are the intersection of a line and one of these guys. So it should be pretty straightforward, and any questions that you have, you probably will find the answers in one of the 3 or 4 examples that they give in section 10.7. So shouldn't be too bad.
Okay.
Okay, let me get you your homework. So I do have special instructions for this homework. So chapter 10, section 7. Okay, and it will be for those, you have that special. Yep. So 1, 5, 9. Oh, and this is on page 467. Chapter 10, section 7, numbers 1, 5, 9, 11, 13, 15, 19. For these, graph it for each one. Graph. And label all intersections. One of the few times I'm ever going to say we don't care about intercepts. I don't care about accurate looking graphs at all. But like we saw, it might benefit you to go ahead and write out a few points, especially if you have like an ellipse and something else, but it's not necessary at all. But I do want again, if you have done something like this and you say, oh, it's going to be something that looks like this and I should have 4 intersection points, and then you go and solve it and you realize, uh-oh, I only got 2 intersection points. I must have had the wrong picture. I'll just redraw it like this, and my thing must have been like that. And then you label the intersections. So you graph the 2 objects that they give you, and you label the intersections as points, x1, y1, x2, y2, just like I did in class. Cool. Okay, last one. Last one is number 21. And it is a multiple choice question. And I would like, so it says, how many points can a parabola and a circle intersect? And then you have 4 options. Option 1 is 0, 1, or 2. Option 2 is 0, 2, or 4, and so on and so forth. Whichever one you select is your final one. What I want is for your final answer, draw an example for each type. So again, to make this clear, what I'm saying is, let's say they ask me how many points can an ellipse and a circle intersect, or let's do one that we did in class, an ellipse and a hyperbola. How many ways can those intersect? And we say, well, what did we see earlier, right? We had this thing that happened here, and one thing was that it intersected in 2 points. Okay, and that would be an example of that type. We also saw that it could intersect in 4 points. And so we said, okay, it could go through like this. And so I don't want an example like with actual numbers. This is what I mean by example. And so you'd say, well, when the type was 2 intersections, I drew it like this. When the type was 4 intersections, I could do it like this. I could say when the type is 0 intersections, it would look like that. That would be 0. And let's see, is it possible that it does 3? Well, yeah, it's like these are all centered at the origin, but there's nothing special about being centered at the origin. What about if I had this guy who happened to be centered at the origin, and then a hyperbola which touches once here, but actually touches twice here? So it's that the hyperbola has been shifted over. Just like, if you took, if you took this guy here, shifted that hyperbola that way until that one point touched right there, well, then we'd have an example of an ellipse and a hyperbola that intersects at 3 points. And so that's what I'd like. It asks you and how many points can a parabola and a circle intersect? There's nothing special about them being at the origin. In fact, you don't even need to draw axes here. I would just like to see examples of, for whatever you get, in this case, it happens to be 0, 2, 3, 4. I could think of 1 actually, like what if, is it possible for it to intersect in 1 place? Well, here's an ellipse. And how about the hyperbola that goes right here? And it's been shifted over so that it looks like this. That's a perfectly good hyperbola. It's just some hyperbola has been shifted. You have an ellipse that touches at one place. And so, yeah, I could think of an example of a hyperbola and an ellipse that intersect at 0 points, at 1 point, at 2 points, at 3 points, and at 4 points. And I've drawn one example of each type. Does that make sense?
Mm-hmm.
Cool. That's what I'm asking you to do for 21. And that is it.